Hi guys, this is A2 Chemistry, Organic Chemistry, and we are looking at organic synthesis. Question 7. The root of the ginger plant contains compounds with medicinal and flavoring properties. Three of the more important compounds are gingerol, shogol, and zingerone. The structure of gingerol is shown. The CH3O group in gingerol is unreactive. Okay, so the structure of gingerol is shown. Gingerol reacts with acidified potassium dichromate. That means it undergoes oxidation. State the type of reaction and the functional group change which occurs during the reaction. So the type of reaction is oxidation, and the functional group changes would be the secondary alcohol, which is the OH group present on the straight chain carbon portion, and it will be converted into a ketone. So from secondary alcohol to a ketone. So that is the oxidation that takes place when gingerol undergoes a reaction with acidified potassium dichromate. The structure of shogol is shown. State the type of reaction needed to convert gingerol into shogol. So the difference between gingerol and shogol is that the secondary alcohol group and the carbon next to it has a double bond present, which means the OH was removed from the carbon with the OH group on it, and a hydrogen atom was removed from the carbon on its left, introducing the double bond. That means dehydration took place. So, state the type of reaction needed to convert ginger into shogol. It's dehydration. State the reagents and condition needed to convert gingerol into shogol. The reagents would be we have either Al2O3, and the conditions would be 350 degrees Celsius, or we would have concentrated H2SO4, and the conditions would be 170 to 180 degrees Celsius. So either of these two conditions could be used. They are not used together, but any one of these two conditions is a dehydrating condition for an alcohol, resulting in the formation of an alkene, as is the conversion from gingerol to shogol. Shogol reacts with hot concentrated acidified manganate 7 ions to form two organic products Q and R. Draw the structures of Q and R. So in order to draw the structures of Q and R, we would need to see the structure of Shogol again. So this is the structure of Shogol, in which we've got a benzene ring with an OH and a CH3O group attached to two carbon atoms. And directly opposite to the OH group, we've got a CH2 and a C double bond O group next to a carbon with that double bond. So the bond that will actually be broken would be this bond. So one of the products would be uh, COOH group attached to the carbon on the left, and a COOH group attached to the carbon on the right. So the carbon on the right would be 1, 2, 3, 4, 5, 6 hexanoic acid, and the one on the left would be the benzene ring with two CH2 groups, a C double bond O followed by a COOH group. So the two structures are the one with the benzene ring, the OH group present here, and the OCH3 group present here, and directly opposite to the OH there were two CH2 groups, and then a C double bond O group, to which we will have the attachment of a C double OH. This is structure Q, and R would be hexanoic acid, so that would be C double OH, second, third, fourth, fifth, sixth carbon atom. So this is hexanoic acid. So these are the two products upon oxidation of Shogol with hot concentrated acidified manganate 7. Zingerone is formed from gingerol. Some reactions of zingerone are shown. Complete the table to identify the functional groups in zingerone. So, benzene diazonium chloride at 5 degrees Celsius and alkaline solution. And the observation is a red precipitate. So, if benzene diazonium chloride is reacting with zingerone, then the functional group in zingerone would be a phenol group, because a phenol reacts with benzene diazonium chloride to form an azo dye, which is a colored dye, and the color here is red. The next reaction is with 2,4-dinitrophenyl hydrazine, which produces an orange precipitate. So that means presence of a carbonyl group. And in the same box, we have warm with tolerance reagent and no change. So if there is no change with tolerance reagent, it is not an aldehyde. In fact, it is a carbonyl group, which is a ketone. So very specifically, it is a ketone group. Question 8. Carvone occurs in spearmint and a stereoisomer of carvone occurs in caraway seeds. Treating either isomer with hydrogen over a nickel catalyst produces a mixture of isomers with the structural formula X. Okay, so all the double bonds have been converted into single bonds, so this is hydrogenation. State the type of stereoisomer carvone can show. The stereoisomerism that carvone can show. So carvone has a double bond present, but it is in the form of a cyclic compound, so it cannot be geometric isomerism. However, it does have a chiral carbon atom present circled in red. So since it has a chiral carbon atom present, it can show optical isomerism. So we can write shade isomerism. It can show optical isomerism due to the presence of a chiral carbon atom. Write an equation using molecular formulae for this conversion of carvone to X. So what they want us to do is to convert the displayed, rather the skeletal formula here into molecular formula. So we need to add up the carbon, hydrogen, and oxygen atoms for carvone and for structure X. So let's do that. So we have in carvone 1 2 3 4 5 6 carbon atoms in the ring, 7 on top, 8 at the bottom, 9 and 10. So we've got C10 here, so we would have C10 in X as well. So that's common. In carvone, the number of hydrogen atoms would be 3 on CH3, then 1 on the C double bond on the left, 4, 2 at the bottom, 5 6, 1 in the red circle, 8. Going down, we would have 9, 10, 11, 12, 13, 14 hydrogen atoms in total. So H14. And on the right side, since we have 3 double bonds that are converted into single bonds, so each double bond will have an addition of 2 hydrogen atoms. So 3 to the 6, so we have addition of 6 hydrogen atoms. So there would be 20 hydrogen atoms in X. In total, there would be 1 oxygen in carvone and 1 oxygen in X. So now since we know the molecular formula of both of these, we can write an equation using the molecular formula. So this would be C10H14O plus 3H2 in the presence of a nickel catalyst. We end up with C10H20O as the product. X can be synthesized from methyl benzene by the following route. So step 1 is electrophilic substitution. Step 2 is also electrophilic substitution. Step 3 is reduction of the nitro group. Step 4 is reaction with HNO2 at temperature below 10 degrees Celsius. Step 5 is hydrolysis. And step 6 is hydrogenation. Okay. So name the mechanism in step 1. Step 1 is electrophilic substitution. What type of a reaction is occurring in the following steps? Steps 3 and 5. Suggest reagents and conditions for each of the following steps 1, 2, 3, and 4. So we are going to look at the flow diagram for the organic synthetic pathway and complete these details. So we need the type of reaction for 3 and 5 and the reaction and conditions for the first 4 steps. So in step 3, we've got conversion of NO2 to NH2. So this is reduction. And step 5 is conversion of diazonium chloride into phenol, which is hydrolysis. The next thing that was needed are the reagents and conditions for steps 1, 2, 3, and 4. So step 1 has an electrophilic substitution reaction taking place between methylbenzene and CH3 twice, then CH and then Cl. So this is the reagent that will substitute hydrogen onto methylbenzene along with the catalyst AlCl3. In step 2, we've got NO2 being added onto alkyl benzene. So the reagents and needed for this are HNO3 along with the catalyst H2SO4, and we need to warm in order for this reaction to occur. Step 3 is reduction. So we need tin plus concentrated HCl for this reduction to occur. Step 4 is the conversion of phenylamine into benzene diazonium chloride. We need HNO2 along with NaNO2 HCl and temperature less than 10 degrees Celsius in order for the formation of benzene diazonium chloride taking place. So these are the 4 reagents and conditions needed for steps 1 to 4 to occur. So the types of reaction and the reagent and conditions have been filled according to what was solved in the organic synthetic pathway. Next, during step 6, hydrogen is added to the benzene ring to produce the cyclohexane ring in X. The six hydrogen atoms are all added to the same side of the benzene ring. State the reagents and condition needed for this reaction. So we need hydrogen and a catalyst of either nickel or platinum metal and a temperature of 150 to 200 degrees Celsius. So these are the reagents and conditions needed to bring about hydrogenation. And the next part says complete the part structure to show the structure of the isomer X that would most likely be obtained during this reaction. Now the statement in part C has said that the six hydrogen atoms are all added to the same side of the benzene ring. So three of them have been displayed here. So we place hydrogen on the same plane, and according to the structure of the molecule of step 6, we have to place a CH3 group here, an OH group here, and a CH bonded to two CH3 groups at this position. So this completes the structure of X. Question 9. Compound J, K, L, and M are isomers of each other with the molecular formula C9H11NO. All four isomers contain a benzene ring. Two of the isomers contain a chiral center. The results of 6 tests carried out on J, K, L, and M are shown in the table. Okay, so on adding cold HCl, J is soluble, K is soluble, L is soluble, and M is insoluble. That means J, K, and L will contain an alkaline group. So if we have got nitrogen and oxygen present, so most likely all three of them will have an amine present. So amine, amine, and amine. and M does not have any reaction with cold HCl. It could either be an acid itself or it could be neutral. So that needs to be figured out. And on adding 2,4-DNPH, we have an orange precipitate formed with J, which means a carbonyl group is present, an orange precipitate with K, which means a carbonyl group is present, an orange precipitate with L, which means a carbonyl group is present, and no reaction with M, that means a carbonyl group is absent. Next, add NaOH and I2. We have a pale yellow precipitate with J, that means CH3 next to the carbonyl group. No reaction, so no CH3 next to carbonyl. Pale yellow with L, so CH3 next to carbonyl and no reaction with M. Warm with failing solution, so not aldehyde for J, aldehyde for K, and not aldehyde for L and M. So heat with NaOH. So if J, K, and L are alkaline in nature, they will not react with NaOH, and P and Q are formed as products on heating with NaOH aqueous, and one of them contains ONA, which means that was the carboxylic part, and the other contains N. That means this is an amide, because an amide would undergo hydrolysis under alkaline conditions, producing a sodium carboxylate and an amine. So P is an amine, Q is a sodium carboxylate. Next is diazotization and addition of alkaline phenol. So this would result in production of a dye if this was phenylamine. So with J no dye produced, with K orange dye produced. So this is phenylamine. No dye produced with L and M. So they are not uh, phenylamines. So they've asked, use the experimental results in the table above to determine the groups in addition to the benzene ring present in each of the four isomers J, K, L, and M. So according to the test results, in compound J, we've got an amine group and we've got a carbonyl group that is next to a CH3 group, and this could be a ketone because we also have no reaction with failing solution. So it's not an aldehyde, so it has to be a ketone. So, and it is next to a CH3 group, so this has to be a methyl ketone. So the two groups in J have been figured out. Next we have in J, and next we have K. K also contains an amine, and according to reaction 6, it is phenylamine. So phenylamine, and we've got a C double bond O group present. That means it is a carbonyl group, and a red precipitated saline solution shows that it is an aldehyde. So this contains an aldehyde group. In L, we've got an amine group, and it is not a phenylamine according to reaction 6. And we've got a methyl ketone present because it is not an aldehyde but a carbonyl group is present. So methyl ketone, that these are the groups present in structure L and in structure M. The only thing we could have figured out with all of these is that it is not an amine, it does not contain a carbonyl group, it does not contain a methyl ketone group, it is not a phenylamine, and the reaction 5 results shows that it is an amide. So the only possible group that we found out for structure M is that it is an amide group, and no other functional groups were identifiable for structure M. Name the type of reaction occurring in test 5 that converts M into P plus Q. So this is alkaline hydrolysis. Suggest structures for compound P and Q. So the molecular formula of P is C6H7 N2. So we have been told that all of the four molecules J, K, L, and M contains a benzene ring. So this would be a benzene ring. So that would cover six carbon atoms and five hydrogen because there is one substitution. So we are left with N and H2. So this is phenylamine. And Q is C3H5O2Na. So one of these carbon atoms would be C double O minus Na plus. So that means we are left with CH3, CH2, C double bond O, single bond O minus and Na plus. It is sodium propanoate. Isomers J, K, L, and M all have the molecular formula of C9H11NO. Use the information in A to suggest a structure for each of these isomers and draw these in the boxes. Draw circles around all the chiral centers in K and L. Okay, so we list down the groups present that we identified in all these compounds. In J, we've got an amine and a methyl ketone. In L, we have an amine and a methyl ketone again. In K, we've got a phenylamine group and an aldehyde. And in M, we just know that we have an amide group present. So these are the structures we need to make, and we also know that all of them contain the benzene ring. So what we do is we draw the benzene ring for all of them. This completes most of the structure. Now to fit in the other functional groups present. So these are the benzene ring for all four of these structures. And now the rest of the molecules. So we have an amine and a methyl ketone. A methyl ketone would mean it is a CH2 with an NH. This would mean the amine and an NH2 group here. And this covers 6 and 1 7 carbon atoms. We are left with two carbon atoms. So methyl ketone would mean a C double bond O here and a CH3 here. So this completes the 9 carbon atoms. In total, hydrogen are 3, 4, 5, 6, 7, 8, 9, 10, 11, 1 nitrogen and 1 oxygen. So this is the structure of compound J. For K, we've got phenylamine. So one of the ends would have an NH2 group directly attached to it, making it a phenylamine. And then we've got an aldehyde group. So now the rest of the molecule will contain three carbon atoms. So three carbon atoms would mean that it can have a CH2, CH2, and CHO group, but it also says that draw the circle around a chiral carbon atom. All the six carbon atoms drawn currently will not be chiral. So in order to make a chiral carbon atom, we need to have a carbon with a CHO group, the aldehyde group, a CH3 group, and a hydrogen atom, making it chiral. So this is the chiral carbon atom in compound K. Next, we have compound L, which also will contain a chiral carbon atom. So it has an amine and a methyl ketone. So having an amine group and a methyl ketone group along with the benzene ring would mean that the one of the carbon atoms has four different groups attached to it. So we make a carbon atom with four different groups attached to it. And this carbon atom would have a benzene ring on one side, an amine group on one side. Now we're left with two carbon atoms, and we have a methyl ketone as well. So a C double bond O and a CH3 group on one side. That would make it uh, nine carbon atoms in total. So the only atom we are left with is a hydrogen atom. So that makes this carbon atom with these four groups attached to it a chiral carbon as well. So this will be the structure for compound L. And now for compound M, we have an amide group present, and we are left with three carbon atoms. So an amide group with three carbon atoms. So and it should not be chiral. So if we convert this benzene ring into a phenylamine as a reactant, that means this is bonded to NH, which is then bonded to a C double bond O group. So now we have covered the nitrogen atom that was required, one of the hydrogen atoms remaining, and a carbon and an oxygen. So what we are left with are five hydrogen and two carbons. So that can fit as CH2 and CH3. And in this way, we do not have any chiral centers present in this amide. So this is the structure of compound M. Compound N is another isomer which has the same molecular formula C9H11NO and also contains a benzene ring. N contains the same functional groups as M. That means it is an amide. N contains, okay, when heated with NaOH, N produces ethylamine and a sodium salt. Ethylamine. Ethylamine. Okay. So CH3, CH2, NH2. This has been produced on hydrolysis, which means what remains is C double bond O, single bond O minus Na plus. This would be the bond that would be broken, the amide bond. And since this covers three carbon atoms, so the only thing remaining is the benzene ring. So we include the benzene ring with the C double bond O, single bond O minus and Na plus part of the molecule, producing compound W. So the molecular formula of compound W would be C6H5 C double O minus Na plus, or rather the chemical formula would be this. Question 10. Compounds W, X, Y, and Z are isomers of each other with the molecular formula C8H7Cl. All four isomers contains a benzene ring. So we're left with two carbon atoms other than the benzene ring in these structures. All four contains a benzene ring. Only one of the isomer contains a chiral center. Okay. The results of six tests carried out on W, X, Y, and Z are shown in the table. So add cold AgNO3. So if we add cold AgNO3, that means if chlorine can be given or chloride ions can be released, then we can have presence of acyl chloride. So white precipitate forms immediately. So this is acyl chloride. RCOCl is present in W. No reaction with X. So if chlorine is not released, that means this is aryl chloride. Aromatic ring. Chlorine is on the aromatic ring. White precipitate forms very slowly. So this is chloroalkane because chloroalkane will release chlorine but slowly. And no reaction with Z would mean that this is an aryl chloride. That means the chlorine is on the benzene ring. So this is the information we have obtained from test 1. Now looking at test 2, heat with NaOH, then add dilute nitric acid and AgNO3. So first we heat with NaOH. That means we are hydrolyzing it. So a white precipitate forms with W. That means on heating with NaOH, it is converted into the RCOCl is converted to RC double O minus Na plus, and Cl will be converted into NaCl, which would form a precipitate with silver nitrate. So no new information obtained here, and no reaction with X would mean that the chloro benzene will not undergo hydrolysis. A reaction with Y means that RCl will undergo alkaline hydrolysis and produce NaCl, which would give a white precipitate with silver nitrate, and Z is again chlorobenzene, so it will not undergo hydrolysis. So no additional information obtained with test 2. With test 3, add NOH and I2. So this will show the presence of a methyl ketone group or a secondary alcohol, which is only there with compound X, which means X contains a methyl ketone group. With test 4, warm with Fehling solution, this will confirm the presence of aldehyde, which is there in compound Y. So compound Y contains an aldehyde group. With test 5, cold dilute acetate KMnO4, the KMnO4 decolorizes with Z. So cold dilute acidified KMnO4. So oxidation occurs. So oxidation will occur in the presence of, and it's cold dilute. So alkene. So this shows that compound Z contains an alkene functional group. Reaction 6. Add aqueous bromine. So no change with the first three compounds. With compound Z, decolorizes and forms a white precipitate. So if it decolorizes and forms a white precipitate, this is a test for the presence of either phenylamine or phenol. And since the molecular formula does not have a nitrogen atom present, that means this contains a phenol molecule. So in this compound, there is an alkene group, there is a chlorine attached to the benzene ring, and then there is an OH attached to the benzene ring as well. Use the experimental results in the table above to determine the groups in addition to the benzene ring present in the four isomers W, X, Y, and Z. So the only thing identifiable in W is the presence of the acyl chloride group. In X, we have identified the presence of chlorobenzene and the presence of a methyl ketone. In Y, we have the presence of chloroalkane and we have the presence of an aldehyde group. So two groups have been identified. In Z, we have the presence of chlorobenzene, we have the presence of alkene, and we have the presence of a phenol group. Isomers W, X, Y, and Z all have the molecular formula C8H7ClO. Use the information in A to suggest a structure of each of these isomers and draw these in the boxes. So all of them have the presence of a benzene ring. So let's draw the benzene ring first, then we will add on the other functional groups as identified from the 6 tests given in the table above. So these are the benzene ring that are present. In Z, because Z has got three functional groups, it is easier to identify them because one of them is a phenol group, so OH directly attached to benzene. Then we have a chloro group that will be present at the 2 or the 4 position. So here I placed it on the second position. And we have an alkene. So the alkene would be CH double bonded to CH2 because we've got in total 8 carbon atoms. So both carbon atoms with a double bond between them. This will be structure Z. Structure Y, we have a chloroalkane and an aldehyde. So only two carbon atoms left. So one of the carbon atoms would be the aldehyde CHO group, and the other carbon atom would be a chloroalkane. So CH2Cl. So this would be structure Y. Structure X would be chlorobenzene. So we place chlorine on benzene. Then we have a methyl ketone. So a methyl ketone would mean that we have a C double bond O group next to a CH3 group. And then we have structure W with the least bit of information. So structure W is an acyl chloride, not an aryl chloride. So that would mean that it would be bonded to CH2, which would be bonded to COCl group. So that would complete the four structures. And the question asked is draw a circle around a chiral center in one of the above structures. So a structure with a chiral center. So a structure with a chiral center is not possible in W, not possible in X, Not possible in Y and not possible in Z. That means one of the structures is not drawn correctly. It cannot be Z, it cannot be W. So we look at X and Y. X is a methyl ketone with a chlorine attached to benzene because that has been clearly identified in the test. So it has to be structure Y. So looking at structure Y again. So if we have a benzene ring with an aldehyde group and a chloroalkane group. So both these groups can be on the same carbon atom. They don't necessarily have to be on benzene. So let's redraw this structure with both the functional groups on the same carbon atom. So benzene on one side, we have carbon, we've got hydrogen on one side, we've got chlorine on one side, and we've got CHO group on one side. So in total, we've got 8 carbon atoms. In total, we've got 5, 6, 7 hydrogen atoms, 1 chlorine and 1 oxygen atom. And at the same time, we have got a carbon atom that is chiral because it has got 4 different groups attached to it. Thus, structure of Y now is correct according to all of the data given in this question. Question 11. The amino acid tyrosine can be synthesized from phenol by the route shown. So, phenol is converted into a compound containing an aldehyde. So, this would have been a chlorine containing compound that would have been attached to phenol. Then we have conversion of the aldehyde into cyanohydrin. So, this is nucleophilic addition taking place. In step 3, the CN is being converted into COOH. So, this is acid hydrolysis of nitrile or cyanohydrin. Then we have PCl5 and water reacting. So, COOH is not converted into COCl. In fact, we have the alcohol being converted into chloroalkane. Okay, okay. So next we've got the Cl being replaced by NH2. So this is the reaction with ammonia. So chloroalkane is converted into an amine. Name the mechanism occurring in the following steps. Step 1 is electrophilic substitution. And step 2 is nucleophilic addition. Suggest the reagents and conditions for each of the following steps. In step 1, the reaction would be between Cl attached to CH2 attached to CHO, and because this is a chlorine containing compound, the catalyst would be AlCl3. In step 2, we have nucleophilic addition taking place, so the reaction is with HCN, NaCN, and HCl acting as a catalyst here. Step 3 would be the cyanohydrin undergoing acid hydrolysis. So we would have HCl plus H2O plus heat under reflux. And in step 5, we have conversion of chloroalkane into amine. So we would have ammonia as a reactant, we would have ethanol as a condition, and we would have heat under pressure as the other condition. Draw the structures of the products of the reactions of tyrosine with an excess of each of the following reagents. So tyrosine is the final product after step 5. So when it reacts with NaOH, the phenol group and the carboxylic group would react with NaOH producing salts. So it would be the benzene ring attached to O minus Na plus in place of OH. Then on the other end, it would have NH2 present as it is, and COOH converted into COO minus Na plus. So this is the product of the reaction of tyrosine with NaOH. Next we have tyrosine reacting with HCl. So the alkaline group would react, which is the NH2 group. So rest of the molecule will remain as it is. The OH group and the COOH group placed exactly where they were without undergoing any reaction, and the NH2 group undergoes a reaction producing NH3 positive, Cl negative, because the amine group being alkaline would react with the acid producing an ammonium salt. So this is the product on reaction with HCl and tyrosine, and with Br2 aqueous. So Br2 aqueous would react with the phenol portion of tyrosine, and bromine would substitute hydrogen atoms at the 2 and the 6 positions relative to OH. So here and here we would have attachment of Br, because on the fourth position we already have the presence of a substituted group. So the fourth position would stay as it is. So we've got two bromine atoms present on the benzene ring attached to the OH group, or the phenol molecule at the 2 and the 6th position relative to the OH group. Question 12. Compound P contains several functional groups. Okay, so we've got chlorobenzene, we've got alkene, and we've got two nitrile groups. Complete the following table to show the structure of the products formed and the type of organic reaction when P reacts with the four reagents. So the first reagent is excess Br2. So when it reacts with an excess of Br2, nothing will happen to the benzene ring. In fact, the double bonded carbon atom would each add on a bromine atom onto it, and the double bond will no longer exist. And in its place, we will have presence of two bromine atoms on the two carbon atoms that had the double bond on them. So this part of the molecule remains as it is. C H C Cn Cn, and we have addition of Br on both these carbon atoms. And the type of organic reaction taking place is called electrophilic addition. Next we have excess hot concentrated acidified MnO4 minus. So when hot concentrated acidified MnO4 minus ion uh, would react, the double bond would rupture, producing two carbonyl compounds. One of them would be the benzene ring with chlorine on it, and a CH and double bond O. This would be a ketone, and the other one would also be a ketone, but with the CN groups being converted into the COOH groups. Because we have hot concentrated acidified gas. The acidified portion would result in the acid hydrolysis of the nitrile groups as well. And the type of reaction would be called oxidation. The next reaction is with excess hot HCl. So compound P has been drawn for ease on the left. So with excess hot HCl, the only groups that would react would be the two nitrile groups, and the two nitrile groups would be converted into carboxylic groups. So the rest of the molecule stays as it is. This is the chlorobenzene part of the molecule. The C single bond H, double bond C remains as they are, and the CN groups are converted into COOH groups. And this reaction is known as acid hydrolysis. The last reaction is with excess hydrogen and platinum as catalyst. So this is called hydrogenation. and hydrogenation of alkene as well as benzene would take place. So the benzene ring would no longer exist because each carbon atom will have a hydrogen added onto it, and the C double bond C would become C single bond C with hydrogen atoms added onto them as well, and the CN group will also be reduced in the presence of hydrogen, converting into CH2 NH2, converting into amines. So CH2 and NH2. So here both the benzene ring and the alkenes undergo hydrogenation as well as reduction of the nitrile group to form amines also occurs, which is known as hydrogenation, and we can include the term reduction in the type of organic reaction taking place because the nitrile groups are reduced into amines.